Strong consistency mode requires a defined set of nodes, or roster. AP mode will allow nodes to join or leave a cluster and guarantees availability. Strong consistency mode allows the cluster members to be modified only by explicit operator intervention. Recall, nodes can have node IDs. You can specify them either as 2 hexadecimal digits or a value that is derived from concatenating the record's MAC address and fabric port number. We're going to use those to construct the roster. The roster is a set of identified nodes that make up a particular strong consistency mode namespace. The way we do that is that nodes are added to the cluster. If we have nodes that are subsequently added to the cluster, they don't automatically extend the namespace without operator intervention. That is, you have to update the roster and then recluster. In fact, the very first time that you set up a strong consistency mode namespace, you have to do just that. How do we handle strong consistency in Aerospike? Aerospike guarantees strong consistency at the record level. First, if you've committed data, it's not lost. Second, there are no dirty reads, so you're not going to read uncommitted data. Third, we can linearize the reads for a client. That is, all the clients see the same sequence of updates. Fourth, we have immediate consistency just as we do for AP mode. That is, you can read the data as soon as it's been written. Fifth, and finally, we can handle clock skew of up to 27 seconds between the nodes, which means clients don't have to do any additional work to figure out how to resolve conflicts. As well, strong consistency is done on a per namespace basis, which means you could have a cluster with different namespace types, some in AP mode and some in strong consistency mode. Aerospike's strong consistency mode is required for modeling certain problems where consistency is required at the expense of availability. Strong consistency mode has 3 partition states. Available, all records in this partition are available for consistent reads and writes. Unavailable, our partition may become unavailable due to network partitioning events. Or dead, our partition data cannot be trusted even though a full roster of nodes are in the cluster. This may happen due to corruption or deletion of storage medium. In strong consistency mode, we have one of 4 record states. OK, replicating, re-replicating, and unreplicated. OK is the normal state, which means that the number of completed replications is equal to the replication factor minus 1. This state applies to both masters and replicas. Replicating is one of the states for the master. The master is in this state if it is in the process of writing to the replicas or proles. Re-replicating indicates that a failure has occurred. We have to recover by re-replicating the data. It's a state on the master. This occurs if the acknowledgments from replicating have not yet been received from all of the proles or replicas. And finally, unreplicated means different things depending on the object. For a master, it means that replication has failed. For a prole or replica, if the replication factor is greater than 2, it means that confirmation has not yet been received from the master. Let's look at how we implement a write transaction in strong consistency mode. In this diagram, we've got a client, a master, and 2 proles or replicas. Vertically, we have time, and what we're seeing here are the states of the master and proles or replicas and messages being sent from one entity to another. We'll start with the state of the record where the master and proles are OK. Initially, the client sends a write request to the master. The master sends writes to the proles 1 and 2. The master then transitions to the replicating state, meaning it is waiting for acknowledgments from each of the proles. The proles receive the writes and send acknowledgments back to the master. The proles then transition to an unreplicated state, meaning they are waiting for confirmation messages from the master. As the master receives the acknowledgments from the proles, it then responds by sending confirmation messages to the proles. When the last acknowledgment is received by the master, it then transitions to OK and sends success to the client. The proles receive the confirmation messages and transition to OK. Note that messages could be lost. This is why we use timeouts on both the client and the master. The client times out if it doesn't receive a success message from the server, which it interprets the record status as unknown. As well, the master could time out, in which case it resends the writes to the replicas and enters the re-replicating state, repeating the above process one more time. If this fails, the master enters the unreplicated state. How do we ensure no dirty reads? That is, that we read only committed data. In this state transition diagram, we've got a client, a master, and two proles or replicas. Vertically, we have time, and what we're seeing here are the states and proles or replicas and messages being sent from one entity to another. We assume the cluster is normal in steady state. There are two cases. The master is OK, in which case we return the record to the client. Or the master is unreplicated. The master retries replication, as previously described, with message passing as described in the diagram. If it succeeds, then the master returns the record to the client and enters the OK state. As before, messages could be lost. The client times out if it does not receive a success message from the server, which interprets the record status as unknown. As well, the master could time out, re-entering the unreplicated state.